I'm going to describe how to use an interactive simulation that models a simple reactor system with a separator, recycle, and purge. And the purge is necessary because this system has an unreactive species in the feed, in this case methane. So this is hydrogen and nitrogen reacting to ammonia. The fractional conversion in the reactor can be fixed, and we're assuming that this can be controlled independently just for the sake of doing these balances. And then the fraction of the exit stream can also be fixed. So the fraction that goes to this purge stream can also be fixed. The separator is assumed to be ideal that it removes ammonia, but only ammonia, and everything else is recycled. So we recycle hydrogen and nitrogen so it can react, and we also have to recycle the methane that's in the exit stream, and thus we have to have a purge stream in order to eventually remove methane from the system. So you notice the flow rate of methane here is the same as the flow rate of methane here. The other two things in this display is the fraction of our feed that's lost to the purge stream. So we're throwing away some of our reactants, hydrogen and nitrogen. In this system, they're fed in a stoichiometric ratio. So we're throwing away some of hydrogen and nitrogen, which of course can be expensive unless we have some downstream process to recover them. And then simulation also lists the ratio of the recycled methane, in this case 33.3, to the methane in the feed, 1.2. So 38.8 divided by 1.2 gives us 33.3. So that's the indication how much of our flow rate that we have to pump around, and this of course affects a lot of things in the system. Let's look at the interactive simulation where what we do is solve the mass balances. These are all linear equations. We solve the mass balances for this system, and we do it for different values of fractional conversion and the fraction of the exit stream that's purged. So here's the interactive simulation. Let's set the fractional conversion at 0.3, and let's make the fraction, the exit stream that's purged, at 0.01. So you'll notice that what this means is that only a small fraction, 2.3% of the feed is actually lost in the purge stream. However, what this means is that the recycle methane to the feed methane is a factor of 100. So we have a very large flow rate of methane in that recycle stream that we then mix with, and of course in a real system this would dilute the reactant concentrations. This would affect kinetics, also affect residence times. Here we're just assuming we could fix the fractional conversion. If we go to the other extreme and have a high fraction that's purged, then the flow rate now is only a ratio of 6.7 methane in recycle to methane in feed, but we're losing more than 25% of our reactant. That's an unacceptable way to operate. Obviously, as we increase the fractional conversion, then we're losing less of our reactant in the purge stream. So hopefully this gives you an idea why we have to have a purge stream, why the purge stream can't be too large, and why it can't be too small.